Welcome to the session on language and bias. We have three works being presented. The first is mitigating racial biases in toxic language detection with an equity-based ensemble framework, and this will be presented by Matan Halevi. So yeah, take it away.
Hi, thank you everyone for attending my talk today. My name is Matan Halevi and I'm a master's student at Georgia Institute of Technology. I'm presenting our work in collaboration with Camille Harris, Amy Bruckman, and Digay, who are also at Georgia Tech, and Ayanna Howard, who's now at Ohio State University. Our work is focusing on mitigating the racial biases in toxic language detection datasets using an equity-based ensemble framework. In recent years, there's been increasing levels of hateful language on social media platforms. In response, these private companies are now using automated moderation to moderate public discourse. However, there's many challenges in using machine learning for this, such as label subjectivity, class imbalances, and annotation biases, which make machine learning systems quite difficult to be fair. Our work is particularly interested in the recent work that has revealed that annotation biases in these datasets exist against users of African American English dialect. When we take the usage of AE as a proxy for race, we see that these racial biases propagate to models through increased false positivity rate. This, as an end result, is a moderation tool that's meant to protect minority groups. Instead, it diminishes their voices and moderates their ability to converse on public platforms. We pose three main research questions. The first is, how do these annotation biases against the AE authors affect machine learning systems trained with them in terms of fairness? Secondly, we want to see the effectiveness of bias mitigation techniques that already exist at reducing the predictive disparities between African American English authors and standard American English authors. Third, we propose a model architecture to help reduce the annotation biases against these African American English authors in the datasets without impacting the general classification performance. Lastly, we also explore bias mitigation through the use of a larger corpus and study the effects of label aggregation across these different toxic corpuses on classifier performance and bias mitigation. So the data sets that we use here, we use 4 publicly available data sets that are derived from Twitter conversations: Davidson et al., Fount et al., Wasim and Havi's the positive subset of it, and Gobek et al. We then use these to create the toxic and hate data sets, using label aggregation on the definition for toxic on abusive language, offensive language, hateful, and also racist and sexist language from the other data sets. For the hate data set, we use Davidson et al., Fount et al., and the Wasim and Havi data set, just for their definition of hate speech, racist, and sexist languages. In the first column, we have the number of samples that are AE, which we derive using Blodgett et al.'s model for dialect estimation. In the second column, we have the toxic samples and the hateful samples in each data set, along with the total samples. Just on the summary statistic of the data sets, we look at the proportion of different dialects being labeled as toxic and not toxic, or hateful as not hateful. In this case, we see that the toxic AE samples always outnumber the SAE samples in quite a significant manner. We don't always see this pattern in the hate definition, though. We also want to note that these data sets are mostly labeled by crowdsourced workers that aren't necessarily familiar with the American English context, and they're taken from around the world. Wasim and Havi, they annotate their data set themselves. So just a warning for offensive language here. I did try to take samples that weren't very concretely offensive, but to demonstrate the difficulty in certain annotations. And so from the data sets here, let's focus particularly on this example here. It was labeled as hate by the annotators. Agreed, relationships would be much better without any men. Listen, I'm not sexist, but no girl should be the man in the relationship. This is labeled as hate. Well, there's definitely toxic underlying, so there's no clear definition to say this is hate speech. So how do we evaluate fairness? Well, with such a high proportion of the tweets already being labeled as toxic, we wanted to look at the predictive parity as well. So we chose disparate impact in this case. Disparate impact is a proportion measurement that looks at the predictive outcomes of both favorable and unfavorable outcomes. What is favorable in abusive language? Well, we decide that as being predicted as not toxic. Over here, typically with disparate impact, acceptable results are between 0.8 and 1.2, and a disparate impact score of less than 1 indicates bias against a protected group, and a disparate impact score greater than 1 is bias favoring the protected group. We also look at the misclassification fairness metrics of false negative rate and false positive rate. Additionally, we evaluate our classification performance using standard metrics of accuracy, recall, precision, area under the operating curve, and F1 score. When we ran our hyperparameter search, we chose a model that had the best F1 score due to the class imbalances that exist in these data sets. So our proposed model we call the hierarchical ensemble model. Our hypothesis is the bias is a direct result of the underlying language models and the data not fully encompassing the distribution of the protected groups, in this case, AAE authors. I'll step through the framework. Given a sample, it goes to a general classifier. This general classifier for us is vanilla BERT, which is a popular language model used in many applications. One noteworthy one is Google search. If it's predicted as non-toxic, that becomes the final output. However, if it's predicted as toxic, we pass it to the Blodgett et al.'s dialect estimation model. If the estimation model decides that this isn't AE, then we pass the final prediction of toxic. However, if it is, then it goes through a specialized learner. The specialized learner, we rerun the mask language model task needed to train BERT with AE non-toxic samples to get a better understanding of the language itself. Then we fine-tuned it with the AE samples present in the toxic data set. We then took the output of this toxic or non-toxic as a final output. To conduct our experiments, we used 7 different algorithms: logistic regression with n-gram, TF-IDF, and glove embeddings, the vanilla BERT that I mentioned earlier, and 2 bias mitigation algorithms. The first one, BERT with explanation regularization, is developed by Kennedy et al. It works by penalizing the model during training for focusing too much on the group identifiers present. This leads well with characteristics of African American English, such as the as camouflage construct and also the usage of the N-word. We then also use BERT with min-def regularization as another bias mitigation algorithm. This takes 2 slices of protected groups and penalizes the models for high disparities in false positivity rates during training. And lastly, we also analyze our hierarchical ensemble framework with BERT. The corpuses we use to benchmark are the Davidson et al., the Fountain et al., and the 2 aggregate data sets that we mentioned earlier. All our results below are reported over 10 randomized seeds, and the errors can be seen in the paper itself. To step through this table here is all the algorithms are given on the left-hand side. We highlight in green the best performing algorithms taken as the ones with the highest F1 scores. Within the best performing algorithms, we then analyze the best fairness indicators. It's worth noting that this data set is particularly difficult to analyze as 98% of the AE samples in it are annotated as toxic. That leaves about 2.5% of the 502 AE samples in our test set as true negatives. In particular, this makes false positive rate, which is often used to analyze these data sets for unfairness, an ineffective measure of fairness. Instead, we focus more on our disparate impact scores here. We see that our model is able to increase the favorable outcome, means that there's more predictive parity across the AE authors and SAE authors. Additionally, it decreases the unfavorable disparate impact. What's interesting to note is that we see an increase in the false negative rate. This could be indicative that our model is actually unlearning some of the annotation biases and disagreeing with the labels provided by annotators in these data sets. We observed similar results with Fountain et al., but the best performing models are again BERT with explanations, and the hierarchical ensemble framework. Again, we see our hierarchical ensemble framework is able to improve the disparate impact for favorable outcomes, decrease it for unfavorable outcomes, and increase again the false negativity rate. Similar to the Davidson et al. Data set, there's a low true negative count of AE samples, where the test set contains 14.5% of 117 AE samples as non-toxic. Next, we look at our aggregate data sets. What's interesting to note here is we notice a lower classification score on the algorithms, which suggests that there might be some label subjectivity issues. In particular, we used a lower threshold of a toxic label versus a hate speech label to try and improve the label agreement across these data sets. But still, it had lower results than individual data sets themselves. We see BERT and our hierarchical ensemble performed best, with the explanation regularization algorithms performing pretty well as well. Again, we notice our hierarchical ensemble framework was able to improve fairness on these data sets with the same pattern of improving the disparate impact scores and also increasing the false negative rate scores. Compared to the toxic data set aggregate, we notice the hate aggregate does not perform well at all, and the models are unable to learn on this data set. This suggests that there's poor label agreement for what constitutes hate speech across these data sets. This is indicative of a larger problem and also poses challenges if trying to correct the problem at the source by providing auxiliary data sets itself, as it has to ensure that there's label agreement. Next, we'll step through some of the challenges that we noticed in classifying toxicity in AE text. We took a random seed and looked at the misclassified samples of AE text, and we grouped them based on how we saw the errors happen. The first one that we'll go through is mislabeled, which our model predicted as non-toxic, and we ended up agreeing with that label. This is one sample where it's not clear where any toxicity comes from. Additionally, we didn't notice that our model still sometimes struggles with the use of curse words or pejoratives for third-party members. Over here, this was labeled as non-toxic by annotators, but our model still struggled with it. It's worth noting this is a popular hip-hop song lyric that was retweeted, and that could be why it was labeled as non-toxic. Additionally, we still see in a similar thing that using curse words in neutral context still makes the model struggle, even if it's not toxic to any particular person or group. And again, there's some missing context, which is a large problem in this hate speech detection. With Twitter, it's only 140 characters, and without proper context, it makes it difficult to analyze why something was determined to be hateful or toxic. In conclusion, we noticed that all our classifiers had higher false positivity rate and lower false negativity rate for the AE instances than the standard American English instances. Additionally, we see the predictive disparity of these biases for both favorable and unfavorable outcomes exist against African American English authors. We note that our proposed hierarchical ensemble framework and the explanation regularization techniques were effective at mitigating some of these bias with minimal impact to overall classification performance. This is particularly important because even though biases exist in these models, it is still important to protect the minority groups that they're designed to. It's also worth noting that our hierarchical ensemble framework could be combined with other bias mitigation techniques. And so we leave that as an open research question. We also wanted to know that 35.3% of the AE instances that were misclassified are likely to be mislabeled by annotators, suggesting that our fairness metrics here are really just lower bound estimates of the true improvement. And finally, we note that the label consistency issues across the aggregate data sets, they lead to poor classifier performance and suggest challenges. If someone wanted to fix a problem on the source of distributing an AE toxic language data set, it would have to work with label agreement across these existing data sets. Thank you very much, everyone.
All right, great. Let's thank our speaker. Fantastic. Yeah, so we actually do have a few minutes for questions. I don't see any that have come through the Q&A Zoom function, but if someone wants to ask one now, that would be cool. I also have a few myself, but it sounds like we have some.
One just came in the chat, I think.
Oh, the chat. Okay, cool. Yeah, so this question in the chat says, hi, I was wondering how the paper weights the false positives and the false negatives. Yeah, could you talk a little bit more about I think what this question is asking is like, what exactly is a false positive and a false negative in this context, and how do you treat these cases?
Sure. So false positive in this context is the annotation in the data set itself is marked as positive, being toxic or hate speech, depending on the data set. And we treat it as a false positive when our predictor has it as positive, but the annotation is actually negative. And conversely, the false negative in this case is when our predictor predicts it as negative and the annotation itself is positive.
Great. Cool. I also, unless there's other folks who have questions, I'm curious to, do you think the misclassifications arise from lexical biases? Like, do you think that these, in particular, large language models are just keying into particular words and using the fact that a word appears to just associate with a particular label? Or do you have an intuition about the failure cases of these models?
Yeah, that's a great question. So let me just figure out how to backtrack in my view here. Oh, too much. Yeah, so there were some examples that were toxic and false positive AE, which were due to the lexical variations that people use to kind of like hide their hate speech. It's common also in eating disorder papers that study that on Twitter, it's very easy to like hide your true messaging by just like switching a few letters around. And so sometimes they get falsely positive as AE by the dialect model here. And that's kind of what results in the false positives. But also in particularly the sensitivity to group identifiers or certain words is also an issue. And so that's kind of what we note in the curse words in neutral context and the pejorative for third parties here. It is something that we're hoping to address with our specialized learner by having more AE samples. The use of the N word in this case is considered appropriate by the in-group. And so hopefully the model becomes less sensitive to it and understands when it's actually offensive and when it's used by the in-group.